Consider this f of g of x model. We've got our domain values of g, say 1, into 2x plus 1 generates a range value of 3. A domain value of 0 generates a range value of 1. A domain value of -1 generates a range value of -1. Now these range values of g become the domain of f. So 3, 1 and -1 are now a part of the domain of f. We substitute those into the f of x model. So 3 goes in and we get a 7, 1 goes in, we get a -1. -1, well -1 isn't a part of the domain of f. The domain of f is x is greater than or equal to 0. So we generated a value that the function f can't deal with. And so that's a typical example of when the composite function doesn't exist. Even though we could work a value out, because -1 isn't a part of the domain of f, then f of g of x doesn't exist. Now that's the key facet, if you like, for the existence of a composite function. The range of the second function has to be equal to or a subset of the domain of the first function. It has to generate values the second function can deal with. Range of g of x has to be a subset of the domain of f of x. Or for g of f of x, the range of f of x has to be a part of the domain of g of x. Okay, so let's consider this example here. We need x is an element of R and x is greater than or equal to 0 for the respective functions. So for the composite function to exist, remember, we need the range of the inner function, which in this case is f, to be a subset of the domain of g. So we need to work out some range values. So the best way to approach these composite function existence is do the little table we've got on the right. So for f of x and g of x, let's identify the domain and range of those respective functions. So we can see for g of x, the domain has got to be from 0 to infinity inclusive. And if we consider the domain of f of x, well, we can see there that it's going to be R. So let's have a look at the range values. Well, for f of x, the function is x squared minus 1, so the range is from -1 to positive infinity. And for the root x function, our range is from 0 to infinity. So let's check the condition. We need the range of f to be a subset of the domain of g, so we need to put the values. So the range of f is from -1 to infinity, and the domain of g is from 0 to infinity. And we can see straight away that that -1 is going to be a problem, so it's false. So the composite function g of f won't be defined. In other words, it doesn't exist. So part B talks about making a restriction for f of x so that g of f is defined. So if we have a look at the range of f, we can see that we need to change the range of f to be from 0 to infinity, or even smaller if you like. But the biggest range of f is going to be from 0 to infinity. So a quick look at the graph of f shows us x squared minus 1. So we need to change the domain just to be positive values. So we can see those red sections there. They're the values that we need to generate. We need to generate that red line. So which x values generate that red line? So that's what we need to consider. So as you look at it, we're clearly going to need some x-intercepts there. So this is where our graph knowledge becomes important. So those x values are from 1 to infinity, aren't they? So it's a section to the right of the graph. Or we could possibly go from -1 to infinity. Sorry, -1 to negative infinity, or minus infinity to -1. -1, obviously. So there's two possible domain restrictions there that we could make. So we'll take the positive one. We could pick either one, but traditionally we take the positive one. So let's restrict the function f, and the new function we'll call it f star, to be x squared minus 1, where x is an element from 1 to positive infinity. Or we could have our domain of being from minus infinity to -1. That's better, as another possible value. Okay, so let's have a look at example 13. Same sort of thing, g of f of x. So we want to do our table of values. So the function f of x, x minus 1, well, obviously it's got a domain of r, and it's going to have a range of r as well. G of x, the graph of x squared, well, again, the domain is r, but the range of that is going to be from 0 to infinity. So g of f of x is substituting the function of f of x into g of x. Okay, so our function there of g of x is x squared, and we're going to put x minus 1 into that. So we can see that, and there's our composite function. Now we could possibly expand it, but we won't. So the domain of that particular graph is the domain of the inner function, which in this case is f, and the domain of f is r. The range of the graph, well, we need to consider what the graph values are. So again, it's a parabola that's been shifted to the right 1 unit. So we can see here from the graph that's coming up that the range of that particular graph is going to be from 0 to infinity. Yeah. Okay, oh well, part B, I guess we should sketch the graph properly, so we'll put our intercepts in, and the x-intercept and the y-intercept. Okay. Example 14 now. So this is a past paper from 2006, which is still relevant to us. We've got to write down the rule of f of g. It doesn't say we need to come up with prove its existence, so we just need a rule. So we just substitute our 2x plus 1 into the graph of x squared plus 1. So we get our 2x plus 1 all squared, substituting that 2x plus 1 there where the x value is. Expand the bracket, group the terms, and that's, either form of it's probably right in reality. We can do a little bit of factorising and take out a common factor if we want, but the original form is probably good enough in this case.